Mr. Clelland here for Clelland Maths. So today we're doing advanced higher maths and we're going to do methods of proof. That's disproven by a counterexample, direct proof, proof by contradiction and contrapositive, and then finally a big one, proof by induction. So hopefully you find this useful. If you do, like and subscribe and watch the advert.
Clelland Maths is sponsored by Lecky, the educational publisher for Scotland. They offer viewers of this channel a massive 30% discount. Just use the discount code ClellandMaths at leckyscotland.co.uk. The practice question books go all the way from level 3 to advanced higher and include National 3, 4 and 5 apps as well, so you can get any book you need for your studies. These are an excellent resource with questions on every topic and contain work solutions so you can see how the marks are awarded. As you go through the book, the questions get increasingly difficult, so by the time you finish your book, you'll be ready for your exams. Usually £9.99, just use the discount code ClellandMaths to get 30% off that. Link down below.
Jumping straight in, find a counterexample to show that this statement is false. Now let's look at some of these symbols. This means for all n, a member of the real numbers, the square root of n squared is equal to n. So we want a counterexample to this. So we just need to find one that doesn't work. Now let me think about this for a minute. If I take a minus number and square it, I get a positive number. So that's probably going to be a counterexample. So let's say let n equal minus 1. Then the square root of minus 1 squared equals 1, which does not equal minus 1, which is what n is. And therefore, by counterexample, I've proved it. Okay, example 2. Find a counterexample to show the following conjecture is false. Let Pn represent the product of the first n prime numbers. So that would be like 2 times 3 for the second one, and then add 1. So Pn add 1 is prime, is to show for all n a member of the natural numbers. So let's just check. Part of the counterexample means you're just going to have to go over and over again. So let's check P1 plus 1. Well, P1 is 2, the first prime number, plus 1 is 3. Well, that's not worked because that's prime. So then we will go on and check P2 plus 1. So P2 is the product of the first prime number and the second prime number, remember, add 1. Well, that's 7, that's still prime. And we keep going, P3 plus 1 is equal to the first, the second, and the third prime number times together, add 1. So that's 15, 30, 31. Well, that's still prime. And you would keep going, P4 plus 1. Well, that's equal to 2 times 3 times 5 times 7, add 1. 2 times 3 times 5 times 7, add 1 is 211. And if you check, that is prime. Hard to check once I get big, actually. But P5 add 1 is equal to 2 times 3 times 5 times 7 times 11 plus 1. You can use a calculator to work that out and you would get 2311. And it's hard to work out, but that is prime. And then finally, P6 add 1 gives me 2 times 3 times 5 times 7 times 11 times 13 plus 1. If you use a calculator to work that out, you get 30031. Now that is not prime, and the reason it's not prime is it is a composite because 30031 equals 59 times 509. So that's not prime. Now, a note on this, we wouldn't expect you to recognise large prime numbers in an exam. So its chances are they wouldn't ask one like this, but it shows off what proof. So just a note on this, the SQA wouldn't really expect you to do this sort of thing in an exam because you wouldn't really expect it to recognise very, very large prime numbers. But it does show off finding counterexamples quite well for this. So we would just say that n equals 6 is a counterexample. And therefore, Pn plus 1 is not prime for all n a member of the natural numbers. And we're done there. Okay, example 3, getting into direct proof. Prove that if A is a multiple of 2 and B is a multiple of 3, then AB is a multiple of 6. This kind of shows off quite well how to write numbers as multiples of other numbers, and we'll get into how to write even and odd numbers soon. But to write that if A is a multiple of 2, that means that 2 divides A. There's a new symbol for you, divides a line. So there exists an M such that, I'll just write such that, M a member of Z, Z being the integers, such that A is equal to 2 times M. So to say that a number is a multiple of 2, you're just writing it as 2 times something or other. So that's basically all that's saying. And similar to show something's in the 3 times table, we're looking for something which is times by 3. So we can just say that 3 divides B. So there exists an N, a different letter, a member of the integers, such that B is equal to 3 times N. So now we've got our numbers written as a multiple of 2 and 3. We have to find out if AB is a multiple of 6. So A times B equals 2M times, dot for times to not make sure we look at x's, 3n. So that's 2 times 3 is 6mn. Well, 6mm. Therefore, 6 goes into A and B. So we can just say as M and N are a member of Z, 6 divides A to B. And we're done there. Prove that the sum of the squares of 2 odd numbers is even. Well, I suppose this is asking us, do we know how to write an odd and even number? So let's say let A equal 2n. That'll give you an even number. So if I add 1 or take away 1, I'll get back to an odd number. That's an odd number. Now you're allowed to add 1 or take away 1, it doesn't matter. Just use whatever one you prefer. I always use add 1, but you can let it be negative if you want. And we're just saying that n is a member of Z, because it's an integer. And then we're going to say let B equal some other number. Let's say K plus 1, where K is also a member of Z. So we've now got 2 odd numbers. These are odd numbers, so we just times them together, square them, whatever it says. Prove that the sum of the squares is even. So we're going to do A squared plus B squared. So we'll just write out what we've got. 2n plus 1 all squared plus 2k plus 1 all squared. So square in the first bracket, you get 4n squared. 2 times 1 is 2, times 2 is 4n, and then plus 1. And similarly, you get 4k squared plus 4k plus 1. And remember, we're trying to make sure that this looks even, so we want to make sure that that gives us a multiple of 2. As long as it's 2 times something, it doesn't matter what it is, it's an even number. So let's just try and tidy this up. We've got 4n squared plus 4n plus 4k squared plus 4k, and then 1 plus 1 is 2. So now 2 is a common factor of everything. So we've got 2n squared plus 2n plus 2k squared plus 2k plus 1. Now that stuff in the middle we know are just numbers because k and n are just integers. So that's 2 times some number, and therefore a squared plus b squared is a multiple of 2, so it's even. So we can just say that. Therefore, a squared plus b squared is a multiple of 2. Therefore, is even. And we're done there. Prove that any multiple of 3 can be expressed as the sum of 3 consecutive integers. Okay, so multiple of 3, so let n equal 3 times some number k, where k is a member of the integers, z. Okay, so now what does that mean? We want to say consecutive numbers. So if I've got k, say for a number, the next number will be k plus 1, the next number will be k plus 2. Or if I want to start with k in the middle, the one before it would be k minus 1, and the one after it would be k plus 1. So there's a couple of ways you can do this. You could write out k minus 1k times k plus 1, and if you add them together, prove that you get 3k back. Or you can start with 3k. 3k equals k plus k plus k. And then does that equal, well, let's take k minus 1 plus k plus 1. Well, I've written it, but is it true? Well, we've got k plus k plus k, minus 1 plus 1 is 0. So yeah, so that's it, we've done it. since we have 3 consecutive integers, we have proved that any multiple of 3 can be expressed as the sum of 3 consecutive integers. So proved. Okay, this is quite a tricky one, this one. We're going to do proof by contradiction to demonstrate that root 2 is irrational. This first came up about 2,500 years ago by the Greek mathematician Euclid of Alexandria. You must have heard of Euclid. So we want to prove that root 2 is irrational. So we're just going to assume that the opposite is true, the negation of it. So we're going to assume that root 2 is irrational and lead to a contradiction or an impossibility, and therefore it must be the opposite. So suppose, for instance, that root 2 is rational. Now we need to know, how do we write a rational number? Now a rational number is defined as any number being written as a fraction. So we're going to let root 2 equal some fraction p over q, where p and q have to be integers. We can't be anything else. It can't be like pi or anything. So we're saying that statement, and now we're trying to say that what can we do with this? So let's square both sides and see what happens. That implies that 2 must equal p squared over q squared if the first statement is true. So we can rearrange that to get p squared. That implies that p squared equals 2q squared. So far, so good. Now we know that since q squared is a member of z, because q is an integer itself, then p squared is even, because we've got 2 times a number, right? And if p squared is even, hopefully you already know this, that implies that p is even. If you take any even number and square it. So what does that tell us? Well, it can tell us that p can be written as some multiple of 2. Therefore, p can be expressed as some multiple of 2, which is a different letter, 2m, where m is a member of z. Okay, so now, what can we do with that? Well, we already know that p squared equals 2q squared. But we're now saying that p is 2m, so 2m squared all squared equals 2q squared, so 4m squared equals 2q squared. So that means that 2m squared equals q squared. Now, that means that q is even, because we can say that since m squared is a member of z, then that means that q squared is even, and therefore q is even. So we now know that essentially, going back to the original statement, if root 2 is a rational number, then it's p over q, and they're both even. So we've just shown that p and q are even, but that contradicts the fact that p and q is a fraction, which has been reduced to its lowest terms. So remember, we already said that let root 2 be a fraction such that p is equal to p over q. Well, when we say that reduced to its lowest terms. Well, since p and q are both even, then it contradicts fact that p over q is a fraction in simplest form, because 2 would go in it. So since we've got a contradiction, our original assumption was false. So that implies root 2 equals p over q is false, and therefore, since it's not rational, it's the opposite, which is irrational. Root 2 is irrational. And we're done there. Okay, example 7, use proof by contradiction to show that there are an infinite number of prime numbers. Like the previous example, this was shown by Euclid around 300 BCE, well, before Christ. Just so you know, the SQA specification says that candidates should benefit from exposure to proofs of root 2 is irrational and an infinite of primes. So that's why we've included them in this video, and maths.scot included on their page 2, an excellent revision website. So what we're going to do is try and assume a negation of what we're trying to prove and follow the steps to get a logical impossibility. So let's assume that there are a finite number of primes, up to n, say. So assume the negation. Assume there are a finite number of primes. So let's just give them a name. So P1, P2, P3, all the way up to some one that we're going to stop at, which would be Pn. Now we're going to say, well, let's take P to be one more than the product of all prime numbers. So let P, big P, equal, I'll write this, one more than the product of all primes. So how do we write that in maths? Then P would equal P1, P2, P3 to Pn, all the way up plus 1. Well, either P is prime or it's not. Now remember what we're trying to say here. We're saying that P up to Pn is the last prime number. So we kind of need to show that P, the product of all that plus 1, is not prime. And if we get to the point where it is prime, then we've contradicted ourselves. That's the idea. So P is either prime or not. So let's just assume both, let's just check both cases. If P is prime, then it is bigger than all our other primes. So in other words, we've found a new prime, so it's a contradiction. So that's us checked what happens if it's prime. But what if it's not prime? Well, if P is not prime, that implies, well, remember our list, that means it's divisible by one of the primes in our list, which we will call P. So that means if P is not prime, that means it must be divisible by some other prime, because remember, all numbers can be made up as a product of prime factors. And we've said that there's only so many of these, it stops at Pn from P1. So if P is not prime, it must be divisible by one of P1 up to Pn. So let's call the one that's divisible by P. So now we need to just check, well, can P be one of our prime numbers, P1 up to Pn? No, it can't. P can't be one of P1, P2, P3 up to Pn. Why not? Because it would divide into 1. So that means that P is a new prime, which again is a contradiction. So we've contradicted both things, and therefore we've reached a contradiction in general, so our assumption must be false, and therefore there must be an infinite number of primes. So therefore there's an infinite number of primes. Now, if you're really interested in this and any of the steps don't follow, just look up proving an infinite number of primes by Euclid to get more information on this. Example 8. Use the contrapositive to prove that if n squared is a multiple of 3, then n is a multiple of 3. So we're looking to see what contrapositive means here. So the contrapositive is using not. So not if n is not a multiple of 3, then n squared is not a multiple of 3. That's our contrapositive statement. Kind of working backwards, n squared is a multiple of 3, then n is a multiple of 3. So if n is not a multiple of 3, n squared is not a multiple of 3. If we can prove that, then by proof by contrapositive, we have actually proved n squared is a multiple of 3, then n is a multiple of 3. So that's what we're trying to do. So we're saying that if n is not a multiple of 3, so n does not divide 3, we'll say f. And we'll consider the two cases. The remainder when n is divided by 3 is either 1 or 2. If you think about it, if you divide a number by 3, it's either going to go in exactly, or you're going to have one remainder, two remainder. So the remainder when n is divided by 3 is either 1 or 2. So let's just check both cases, right? So remainder 1. That implies that n equals 3k plus an extra 1 for some k a member of z. So in this case, n squared would be 3k plus 1 all squared. Well, that equals 9k squared plus 6k plus 1. Now all we need to say is that 3 times the number plus 1? We'll just take 3 out as a common factor and leave the 1 on the end. So that equals 3k squared plus 2k, with an add 1 sitting about on the end waiting. So n squared is 1 greater than a multiple of 3, so that means that 3 does not divide n squared. One greater than a multiple of 3, then for 3 doesn't divide n squared. And then we'll just check what happens when the remainder is 2. So for remainder 2, n must equal some number 3k plus 2 for some k a member of z, and that means that n squared would be 3k plus 2 all squared, which is 9k squared. 3 2s is 6 times 2 is 12k plus 4. So again, can we check to see if that equals plus 2 or something? So what does that equal? 3 times what? Well, 3k squared plus 4k. We can take out, well, 3, and we can take out a plus 1 here. 3 ones is 3, and then have 1 on the end. So we've still got a remainder of 1 at the end. So in this, the second case, n squared is 1 greater than a multiple of 3. Therefore, 3 does not divide n squared. So we've exhausted both of the cases, and each of them 3 didn't divide n squared. So we've proven that if 3 doesn't divide n, it doesn't divide n squared. So the contrapositive is true. We just need to write that down. So we have proven that if 3 doesn't go into n, then 3 doesn't go into n squared, and therefore we have by the contrapositive, which we would need to write, if 3 divides n squared, then 3 divides n, and we're done there. Example 9, prove by contrapositive that if PQ is irrational, then at least one of P or Q is irrational. So what is a contrapositive statement? If both P and Q are rational, then P and Q is rational. So let's write out a contrapositive statement. If, now or becomes and, both. If both P and Q are rational, then P times Q is rational. So what does it mean for P and Q to be rational? It means we can write them as fractions. P is equal to some number A over B, and Q is equal to some number C over D, where A and C we would want to be integers. It can be anything, positive or negative, but we want B and D to be natural numbers because we don't want to get a negative divided by a negative. So we've got that. What is P and Q? Well, P times Q is A over B times C over D. That's AC over BD. Well, what's our top? Our top's an integer, which times an integer together, and our bottom's a natural number. So that's also a member of Q. Just by looking at it, okay? And we've just then therefore proven that if P and Q are a member of Q, then PQ must also be Q. P times Q is also a member of Q. So by the contrapositive, the opposite is true. So by the contrapositive, if PQ are not rational, so not, then P times Q is not rational. And we're done there. Example 10, prove by induction that for all, that's what that says, n, a member of n in natural numbers, 6 to the power of n plus 4 is divisible by 10. So induction is this. It's like a snowball effect. We prove that n equals 1. We assume it's true for some random letter like k. And if we can then prove that it's true for the next one, it's true for the one after and the one after and the one after. But since the first one was true, it's true for all of them. So it's kind of just a process you need to work through. So let's look at our base case, which is n equal to 1. We'll just do the left-hand side. 6 to the power of 1 plus 4, well, that equals 10, which is clearly divisible by 10. So, well, let's assume it's true for n equal to k. So assume true for n equal to some letter k. So that means we're saying that 6 to the power of k plus 4 is divisible by 10, divides that, or is divisible by 10 for some k, a member of the natural numbers. We're just assuming that's true, and we're now going to try and show that 10 also divides 6 to the k plus 1 plus 4. We're going to show that 10 goes into 6 to the k plus 1 plus some 4. So let's just look at 6 to the k plus 4 to start with. So we've got 6 to the k plus 4. We know that's divisible by 10, so we can say it's 10 times a number. Let's say it equals to 10a, and that will be for some a member of z. That means we can rearrange for the k part to get 6 to the k is 10a minus 4. So far, so good. So what's 6 to the k plus 1 plus 4? Well, 6 to the k plus 1 plus 4, we kind of want to get a 6 to the k out of that so we can sub it in. Well, 6 to the k plus 1 is just 6 times 6 to the k. Rules of indices, that's a 1, k plus 1 plus 4. But we know what 6 to the k is 10a minus 4. So that's 6 10a's minus 4 plus 4. If we can show it that's a multiple of 10, we're done. So just span it out. 60a minus 24 plus 4. 60a minus 20. And we just need to show that 10 is a factor of that. Well, that is equal to 10 times 6a minus 2. A was an integer, so that means that 6a minus 2 is also an integer, and therefore 10 divides 6 to the k plus 1 plus 4. So we've now proved it because we've got 10 times an integer. So that means we can just say proposition, if proposition true for n equal to k implies it's true for n equal to k plus 1. You can write the word implies if you want. And base case is true for n equal to 1. Then by induction, it's true for all n. For all n, a member of the natural numbers. And we're done there. Now watch out, you do need to write your statement. You need to say if the statement is true for some n equal to k, implies that it's true for some n equal to k plus 1, and we'll prove the base statement, then by induction, it's true for all n. Okay? The Fibonacci sequence is defined by the recurrence relationship f1 equals f2 equals 1. We already know that, 1, 1 in other words. And then fn plus 2 equals fn plus 1 plus fn. What is it trying to say here? Well, it's saying that if we take, say, f3, it's f2 plus f1. It's just the previous two added together. That's what the Fibonacci sequence is. And it's saying that we have to prove by induction that for all n a member of the natural numbers, if we add up all the Fibonacci numbers, it's actually just equal to fn plus 2 minus 1. So we're just going to do it by induction, so base case. In other words, n equal to 1. So just looking at our left-hand side, we've got f1, which is equal to 1. And our right-hand side, well, f1 plus 2 minus 1, f3 in other words, we've got 1, 1, 1 plus 1 is 2. So that's 2 minus 1, which equals 1. So true. And then we'll assume it's true for n equal to k. So what we're saying here then, we're saying assume that f1, f2, f3, all the way up to sum k equals f k plus 2 minus 1. And that's assuming that k is a member of the natural numbers, of course. So we've assumed that. And now we'll just try and prove the k plus 1, n equal to k plus 1. Then we've got f1 plus f2 plus all the way up to fk plus the next one, which is fk plus 1. That's what we're trying to look at. Now, we already know what f1, f2 up to fk is, so we can just sub it in. We can just say that that equals fk plus 2 minus 1 plus fk plus 1. So that's fk plus 2 plus fk plus 1, all minus 1. What's fk plus 2 plus fk plus 1? K plus 1 plus k plus 2 equals the next one, k plus 3. fk plus 3 minus 1. Now remember, we're trying to show that we're trying to get fn plus 2 minus 1. Well, what's fk plus 3 in that term? Well, fk plus 3 equals fk plus 1 plus 2. Look, plus 2, yep, minus 1. So it's now true for f up to k plus 1, because we'll say that f1 up to fk plus 1 equals f of k plus 1 plus a 2 minus 1. And therefore, we can say it's true for everything. So we just need to write our statement now. Proposition true for n equal to k implies true for n equal to k plus 1. Base case true for n equal to 1. By induction, true for all n a member of n. So we've said true for n equal to k implies true for n equal to k plus 1, and with the base case is true for n equal to 1, and therefore it's true by induction for all n. Example 12, SQA Advanced Higher Maths 2016, question 5. Prove by induction that the sum of r equals 1 to n of r 3r minus 1 equals n squared times n plus 1 for all n a member of the natural numbers. So again, induction, so we're going to do base case first. N equal to 1. So our left-hand side gives us the sum of r equals 1 to 1 of r 3r minus 1. Well, that equals just 1. R is just 1 then, because it goes 1 to 1. That's 1 times 3 times 1 minus 1. So that's 1 times 2, which is 2. There's our left-hand side. And our right-hand side, 1 squared, 1 plus 1 is 1 times 2, which is 2. So true. And we're going to assume it's true for some n equal to k. K is a member of the natural numbers. So that means we're saying that the sum of I equals 1 to k of kr 3r minus 1 equals k squared k plus 1. That's true. And then we're going to try and prove it's true for n equal to k plus 1. So that means we'll try to prove that r equals 1 to k plus 1 of r 3r minus 1 equals k plus 1 all squared times k plus 1, k plus 1. So we'll just deal with our left-hand side first and try and get to the right-hand side. So this is one of these ones where you play about with summations. We want to know what that is in terms of the one above. So that equals the sum of r equals 1 to k of r 3r minus 1 plus the next one. So the next one is just putting k plus 1 into here. And that's a trick. So plus k plus 1, 3 times k plus 1 minus 1. And then we can just play around with that. So that equals, well, we know what the sum part is. It's k squared k plus 1. And then we've got plus k plus 1. And then we've got 3k. 3 ones is 3 minus 1 is 2. And eventually, remember, we're trying to get it to go down to k plus 1 all squared, because that'll be n, would be k plus 1, and then k plus 1 plus 1, which is k plus 2. So that's what we're trying to get to. So let's just expand it and correct it and see what we get, or factorize it, whatever we can do. Well, I can see that we've got a common factor of k plus 1, so I might as well try factorize. K plus 1 is a common factor to give k squared from the first term, plus 3k plus 2 for the second term. That gives me k plus 1, k squared plus 3k plus 2 is going to give me double brackets actually, 2 and 1, and plus and plus. So that's 2 brackets of k plus 1 all squared, times k plus 2. So that's exactly what we're looking for. K plus 1 all squared times k plus 2. So therefore, we can just say it's true. So proposition true for n equal to k implies true for n equal to k plus 1. Base case of n equal to 1 true. Therefore, by induction, true for all n a member of the natural numbers. And we're done there. Example 13, SQA Advanced Higher Maths 2019, question 14. Prove by induction that the sum of r equals 1 to n of r factorial r equals n plus 1 factorial minus 1 for all positive integers n. So again, we'll start with a base case of n equal to 1. So we've got the sum of r equals 1 to 1 of r factorial r, well that's just 1 factorial times 1, which is just 1. And then the right hand side, we've got 1 plus 1 factorial minus 1, 2 factorial minus 1 is 2 minus 1 is 1. So true for n equal to 1. Assume true for n equal to k. So the sum of r equals 1 to k of r factorial r equals k plus 1 factorial minus 1. For some k, a member of the natural numbers, or z plus, then positive integers, same thing. So then we're going to try and prove that the sum of r equals 1 to k plus 1 of r factorial r equals, well, what's it going to be? K plus 1 factorial minus 1. Well, let's just see what that is so we know what we're aiming for. That's k plus 2 factorial minus 1. So we'll deal with our left-hand side. So looking at our left-hand side, and we'll try and make it look like our right, r equals 1 to k plus 1 of r factorial r. Well, we can use our r equals 1 to k of r factorial r, and then just add the k plus 1th term. So that means we've got r factorial becomes k plus 1 factorial, and r becomes k plus 1. But we already know what the sum is. It's k plus 1 factorial minus 1. So that equals k plus 1 factorial minus 1 plus k plus 1 factorial, k plus 1. And we should be able to see here that k plus 1 factorial is a common factor between these two things. K plus 1 factorial is a common factor. So we can say we've got k plus 1 factorial k plus 1 factorial times 1. And then for this term, we've got plus times k plus 1. And the thing we didn't factor out was the minus 1, so it's just hanging out in the end, waiting to be dealt with. So that equals to k plus 1 factorial times k plus 1 is k plus 2, all minus 1. Well, remember we're trying to get to k plus 2 factorial minus 1, but that is that. If you've got k plus 1 factorial, and then you times by the next one, you've got k plus 2 factorial. So that is equal to k plus 2 factorial minus 1. Then we just write our statement. Proposition true for n equal to k implies true for n equal to k plus 1. Base case of n equal to 1 true. Therefore true for all n a member of the natural numbers, or z plus. By induction. I forgot my induction, honestly. I should have probably written that first. So by induction true. But therefore, that's fine enough. Example 14, SQ Advanced Maths 2023, Paper 1, Question 8. Part A. Consider the statement for all integers a and b, if a is less than b, a squared is less than b squared. Find a counterexample to show that it is false. And then part B. Let n be an odd integer. Prove directly that n squared minus 1 is divisible by 4. Let's deal with these separately then. Let's go for a first. So we want to pick a number a less than b such that a squared is less than b squared. Now let's think about positive numbers first. See how you would work through this. Let's pick 1 and 2. 1 1s is 1, 2 2s is 4. It's not going to work. What about negative numbers then? That's going to give us something. Let's say that a was minus 1 and b was 2. Well, minus 1 squared is 1. 2 2s is 4. That's not worked either. But what about a being a bigger negative number? So let's say we had a was minus 3. Minus 3 squared is 9. Then all I need to do is pick a b smaller than a b bigger than that, any positive number, which is about 1 or something, and then we'll be done. So let's say let a equal minus 3 and b equal to 1. Then minus 3 is less than 1, but minus 3 all squared is 9. 1 squared is 1, and 9 is not less than 1. And we're done there. Therefore, false. Okay, part B. Let n be an odd integer. Let n be an odd integer. Remember, that's how you write an odd. Prove directly that n squared minus 1 is divisible by 4. So we want to prove that. If we take n squared minus 1, you get a multiple of 4. 4 times anything. So let's just look at n squared minus 1. N squared minus 1 equals 2k plus 1 all squared minus 1. That's 4k squared plus 4k plus 1, then minus 1. Well, that's just 4k squared plus 4k, but that's a multiple of 4. Don't take out k as a common factor. You only need to take out your 4. Since we know that 4 is 4 times k squared plus k, that's a multiple of 4. As k, remember, was a member of z. So you're doing, if k is an integer, k squared plus k is also an integer, of course, a whole number. So that means that 4 times a whole number is a multiple of 4. So therefore, true. Therefore, what we're trying to prove again, that is divisible by 4. Well, that's it. Done. Consider the statement for all odd numbers n squared plus 4 is prime. Find a counterexample to show that the statement is false. Nice and simple, this one. We just need to find the number odd. So we just try it in our heads. 1 squared plus 4 is 5. 3 squared is 9 plus 4 is 13. 5 squared is 25 plus 4 is 29. 7 squared is 49 plus 4 is 53. 9 squared is 81 plus 4 is 85. Oh, that's in the 5 times table, so it's not prime, so let's just write that out. So for n equal to 9, 9 squared plus 4 equals 85, which is not prime, as you can find the number 5 times 7 equals 85. So we've proved it by counterexample. Okay, part B. Prove directly that the difference between the cubes of any two consecutive integers is not divisible by 3. So let's take an integer, any one we want. Let's call it n. Then the next consecutive integer is clearly n plus 1. N plus 1 cubed minus n cubed. Expanding n plus 1 cubed, we get n cubed plus 3n squared plus 3n plus 1 minus n cubed. We've used Pascal's triangle for that. That implies we've got n cubed minus n cubed is nothing. We've got 3n squared plus 3n plus 1. Should be able to see then there that we've got 3 bracket n squared plus n plus 1. So let's just call that m. That's 3 times m. So 3m is divisible by 3. And therefore, obviously, 3m plus 1 is not divisible by 3. As there is a remainder of 1. Always a remainder of 1. The difference between the cubes of two consecutive integers is never divisible by 3. Done. SQL Advanced Maths 2023, Paper 2, Question 12. Prove by induction that for all positive integers n, the sum of y equals 1 to the n of 2 to the r minus 1 times r is 2 to the n minus 1 plus 1. So let's prove it for n equal to 1. Let's prove. And then we'll do for k, and then k plus 1 should follow. So for the left-hand side, we get r equals 1 to 1 of 2 to the 1 minus 1 times 1. Now that gives us 2 to the 1 minus 1, 0, so 2 to the 0 times 1, which is just 1. And the right-hand side should follow. We get 2 to the n equals 1, 1 minus 1 plus 1. That's 2 times 0 plus 1, which equals 1. So it's true for n equal to 1. And now we're going to assume it's true for n equal to k. So assume true for n equal to some number k. So we can write the sum, that means the sum of r equals 1 to k of 2 to the r minus 1 times k times r equals 2 to the k minus 1 plus 1. And now we want to prove it for n equal to k plus 1. So we're going to prove for n equal to k plus 1. So let's look at k plus 1 then. Looking at our left-hand side, that will give us the sum of r equals 1 to k plus 1 of 2 to the r minus 1
times r. And the game here is, I suppose, to pull this out to see if we can get some sort of composite sums that are add or take away, but we already know the answer to. So what does that equal? Oh, equal the sum of r equals 1 to k of 2 to the r minus 1 times r plus the k plus 1th term. Well, what is the k plus 1th term? It's going to be 2 to the k plus 1 minus 1 times k plus 1, because that's the k plus 1 when that r is k plus 1. So then we'll just tidy that up. We already know the sum of r equals 1 to k of 2 to the r minus 1 times r, because we said it was true for n equal to k, so we can sub in this right hand side. So that gives us 2 to the k minus 1 plus 1. Plus r. Now we can tidy this up slightly. That's k plus 1 minus 1, which is 2k, just k, 2 to the k times k plus 1. So we've got 2 to the power k as a common factor. We can just leave the 1 on the end. So that means we've got 2 to the power k, and we've got k minus 1 plus k plus 1. And we've got our plus 1 hanging around the end. So we can tidy that big bracket up. We've got k plus k is 2k, minus 1 plus 1 is 0, plus 1. 2 to the k times 2k, well, basically that's 2 to the 1, so we can add the powers, so that gives you 2 to the k plus 1 times k plus an extra 1 on the end. So that's our left-hand side. Now I suppose it's worth looking at what our right-hand side would be. So if we look at our right-hand side of this, we have got 2 to the n minus 1 plus 1. Let's just write that down. 2 to the n minus 1 plus 1. So this doesn't look quite like that, but when n equals k plus 1, that implies we get 2 to the k plus 1, k plus 1 minus 1 plus 1, which is the same as 2 to the k plus 1. K plus 1 minus 1 is just times k plus 1. So we've got the same result from the left and the right, and therefore the sum of r equals 1 to k plus 1 of 2 to the r minus 1 times r equals 2 to the k plus 1 minus 1 plus 1. Just write a little statement to say it's true for n equal to k, and implied it was true for n equal to k plus 1. And since it was true for n equal to 1, then by induction, it will be true for all n a member of Z plus. And we're done there. SQA Advanced High Maths 2024, Paper 2, Question 11. Consider statements A and B below. For each statement, if true, provide a proof, and if false, provide a counterexample. Okay, statement A. The sum of the squares of any two consecutive numbers is always prime. I'm thinking Pythagoras here. 3 squared plus 4 squared equals 25. Well, 25 is not prime. There you go, counterexample, job done. 3 squared plus 4 squared equals 9 plus 16 plus, which equals 25. 25 is not prime, therefore it's false. I'm sure there's other examples, but that one will do. Okay, the sum of any two consecutive integers is always odd. Let's see if that is true by saying that, look, let's let n be an integer, and then the next one is n plus 1 then. So you're going to have n squared plus n plus 1 squared. And just a reminder, looking at odd, the form you're looking for is 2a plus 1 is odd, or 2n plus 1, whatever. Expanding the bracket, we get n squared plus 2n plus 1, which is 2n squared plus 2n plus 1. So taking out a common factor with 2 from the front bit and the n, or just 2 even, we'll get n squared plus n plus 1, and that's just a number. So that's just basically of the form 2a plus 1, so we can just immediately say that equals or is of the form 2a plus 1, therefore odd. So statement true. And we're done there.
This has been Clelland Maths today. We've done the whole of Advanced Higher Maths Proof. Hopefully you found that useful. Take care, stay safe, and goodbye.